So we already mentioned a bit of counting. Here's the two kinds of counting that have come up implicitly already. First, if G has n vertices, then we can tell you what the maximum number of edges is. It's n choose 2, because the edges are just pairs of distinct vertices, and you can pick any pair. There's no ordering involved, so it's a size 2 combination, subset of size 2, and you count those with n choose 2. If you pick every single one of them, make every single edge that you can, you call that the complete graph. And it's got the usual notation is capital K sub n. K for complete, I guess. Well, probably in German. For two graphs, G and H with n vertices each, we did mention that there are n factorial possible bijections. So you can see that by just taking the vertices of G one at a time and counting how many ways that they can be mapped to an output vertex in H. So n factorial gets to be a pretty large number, and I mentioned that we could check them all to see if there's an isomorphism between G and H. And to check them all, we'd write them all down and then one by one check to see if all the edges are if and only if. That takes a long time. You can write a computer to do that, and so it's always possible. But to check all n factorial possible bijections, I mean, with luck and some intuition, you can find the one that works quickly. The problem is, if there is none that works, then worst case scenario, you have to check them all to be sure. So we look for shortcuts. If G is not isomorphic to H, so there is no bijection that works, we might not have to check all n factorial bijections if instead we could find invariants. So invariants are exactly what is implied by that paragraph. And so let's look at an example of invariance first, and then I'll define it by example. So definition, the degree of a vertex in G is the number of edges which include that vertex. So in the picture, they're the number of edges that touch it. So here's an example of some degrees just to look at. Here's G, and it has A, B, C, D, and E as vertices. Notice that A isn't connected to anything. That can happen. But the rest of them have some edges. And so here's the degrees. The degree of A is equal to 0 because there are no edges that include it. And then degree of B is 3. You can see 3 edges touching B. C and D both have degree 2, and E has degree 1. So we write those down. The degree sequence of G is the list of degrees from largest to smallest. So you can abbreviate that degree sequence of G. And I looked at all the degrees, and there's the list from largest to smallest, 3, 2, 2, 1, 0. So it's an ordered list. You can think of it as a vector or just a string of numbers. Thinking of it as a vector, 2 of those are equal if they have all the same components, all the same entries. And that's what we're going to use for our first invariant. So here's the theorem that is the prototype theorem for invariance. If G is isomorphic to H, then degree sequence of G equals degree sequence of H. So degree sequence is a graph invariant. And a graph invariant is defined by just replacing degree sequence in that theorem with any function of any kind, as long as you know how to define when they're equal. So in general, it says if G is isomorphic to H, then function of G equals function of H. That function is a graph invariant. This time the function is degree sequence. Now here's how you use it. You always use it to show that G is not isomorphic to H. You can definitely use it to show that they have the same degree sequence, but that's going the long hard way, because finding out that they're isomorphic might take a while, and finding the degree sequence is fast and easy. So practically, you find the degree sequence first, but then you're only interested in the contrapositive of the theorem. Degree sequence of G is not equal to degree sequence of H implies that G is not isomorphic to H. The contrapositive is always equivalent, logically, to the original conditional. So let's see an example of that. Here's G and H. You should cover up the bottom of it and see if you can get the degree sequence on your own. But I went ahead and wrote them down. They're not too hard to find. Just have to carefully count and make sure you don't overcount or undercount any of the vertices. So you get 4, that would be the vertex A. 3, that would be C. And then a couple of 2s and a 1 for G. And for H, we have 3, 3. 1 and 2, both the vertices number 1 and number 2 both have 3 edges touching. And then 2, 2, 2. So those two sequences are both length 5, but they're definitely not the same. So since they're not the same, we conclude G is not isomorphic to H. No matter how hard you look, you cannot find a bijection between G and H, the vertices, which respects the edges, takes edges to edges. Even though they have the same number of vertices, 5, and the same number of edges, 6, they can't be isomorphic because their degree sequences are not the same. Here's another example, another G and another H. And this time, however, they both have the same degree sequence. The first one has 3, 3, 2, 2, 2. The 3s are the vertices E and C. And the second one has 3, 3, 2, 2, 2. Here the 3s are vertex 2 and vertex 5. But, question, does degree sequent G equal degree sequent H imply that G is isomorphic to H? Answer, no. The converse of our theorem is not true. This is often the case with invariance. Invariance being, practically speaking, something which is easier to calculate than checking all the possible bijections to see if it's an isomorphism or not. And they are often useful in the contrapositive. If the invariants aren't equal, then the originals aren't isomorphic. But they're often not very useful in the forward direction. Degree sequent G equal degree sequent H. Well, that's actually the converse direction. That's what I mean. They're not useful in the converse. The converse of this theorem that we have is not true. Those two graphs above, G and H, are in fact not isomorphic, even though they have the same degree sequence. But we'll need something else to see that they're not isomorphic. One thing we could do is check all 120 bijections and see that none of them obey our rule. But there are lots of invariants, lots of graph invariants out there, and we could find another one that works even though degree sequent doesn't. So if an invariant happens to work both ways, so that means it's described with if and only if in the original theorem, then you have a special word for it. It's called complete invariant. Second time we used the word complete here today, but that's a coincidence. It's complete invariant if it's an if and only if. Now, usually that means it's almost as hard to calculate as checking the original isomorphism. So it's hard to find a complete invariant, which is also an easy invariant. But an interesting question is there a complete graph invariant out there? And what would that be? So I'm not completely sure. I'd have to Google it myself. Usually we work with not complete invariants, like the degree sequence.